I wanted to do a related rate problem for you. So this is 352. It's a water tank. It's an inverted cone, and water is flowing into it at a constant rate. So if we're going to draw, you could draw a picture of this. The key issues are the radius and the height. And we know, if we look at this problem, there are a couple of things. First, if I call the maximum radius 6 feet, I'm going to call that R. I'm going to call the maximum height 8 feet. Then, because this is a cone, we know that at any other point on the cone, when you're at a given height, h, that is related to the radius at that height by the ratio of the maximum height over the maximum radius. And so it's just similar triangles. So little h over little r equals big H over big R. And so that gives us the relationship between H and R. And if we were looking at, okay, so what is the volume? If you remember your volume equations, right? It's 1/3 pi r squared h is the volume of the cylindrical cone. At height r, or at height h, right, which corresponds to radius r. And so what we want to do is express this just in terms of h, right? Or just in terms of r, pardon me. And so I'm going to go back up here, and this equation we really need to write as r equals h onto r over h, right? And so we can put this in, and we get our volume is 1/3 pi h which is just going to be 1/3 pi r over h squared times h cubed. So the volume goes as h cubed. Okay, so now we need to take the derivative with respect to time. So v prime, derivative of the volume with respect to time, which we know is 4 cubic feet per minute. That's a constant, equals, taking the derivative of h cubed is going to be 3h squared dh dt. So the 1/3 and the 3 give us 1 squared times h squared times dh dt. And now we can solve for dh dt. Right, is 4 cubic feet per minute times 1 over pi times h over r squared times 1 over h squared. And if we want to evaluate this when the height is, this is the change in height of the water, we know the volume of the water is changing at a constant rate of 4 cubic feet per minute, because that's where we're adding We can stick in the 3 feet in the problem and get what the instantaneous change in the height is when you hit 3 feet. You can see, as expected, when you go to 4 feet, that DHDT will be smaller. That's what you expect, because as you fill the cone, it's getting wider and wider and wider as you go up in height, and so it takes more water to increase by an inch or by a foot in the tank. And so 3, it's the height is changing faster than at 4, which is changing faster than the height at 5. And that would be it for this problem.